Not sure? Alright, Kelsey, what you got?
We just add 5 to 16.
Okay.
You get 21. And
So 3x needs to be greater than 21?
yeah, and I just divided it and it just equals 7.
Okay, so when I divide by 3, and so we're going to talk more about this a little bit later, I get x. Now you said equals 7, is that what it is? X is equal to 7?
No.
No, what is it?
X is greater than 7.
Greater than 7.
X is greater than 7.
Plus.
Okay? So you kind of took some algebraic steps there to work this inequality out. So does this inequality agree that x equals 7 is a solution?
No.
No.
Why not?
Like I said, the answer is going to be greater than 7.
The answer's got to be greater than 7. Is 7 greater than 7? No?
No?
So we're
It'll
thinking
be-
false now?
Yeah.
Yeah. Did anybody discover an easier way to realize that it was false? What you got, Ralston?
Let me click this here.
Say it again.
Okay, friend, look at your paper.
I said, let me go back.
You good?
I forgot how to figure it out.
Okay. Does anyone have maybe an easier way to figure it out that it's a false statement?
Yeah, you just plug in, yeah. You just plug
Oh.
in any number.
Because
No,
the
it's
key to this is what word? What are we trying to determine? If it is a,
True.
the word true is not up here, it is a solution.
Solution.
But what does it need to make the inequality to be a solution?
That's right.
Anything greater than 7.
Well,
Anything that makes it
I
true.
remember
it's
that.
anything, any value that makes that inequality
True.
true.
So anything greater.
So remember, you don't have to show all the work to determine if one single number is a solution.
8 and more.
21 minus 5 is greater than 16. Is 16 greater than 16?
No.
No, that's why I
That's,
thought.
that is a false statement. So is it a solution?
No.
No. We good with that? Alright, really quickly though, I do want to say, Bree, you said 8 and up,
And
right?
8 and-
What about 7.1? Would that be a solution?
Yeah.
Yes.
So does it have to be 8?
No, it can be
It
greater
has to be
than
greater
7.
than 7. So could it be 7.001?
No.
Yes.
Yeah.
Oh, yeah.
I mean, is that greater than 7?
Yes.
Yeah.
So that's an important thing to recognize, that it doesn't have to be 8. We're used to thinking about integers, right? 7, 8, 9, 10, so on and so forth, but we can definitely get
Yes.
rational and irrational numbers as well, those decimals in there. Yeah. Any questions about that before we move forward?
You see how long I told you it won't take? 2 minutes.
Yeah, but 1.3 would have taken longer. All right, so here we are all over the place with our answers, which is kind of what I expected. It's exactly what I saw in first block today. So the question was to identify the type of question, type of data. What is, that should just say Mr. Kenny's, not the Mr. Kenny's. What is Mr. Kenny's favorite board game? I got a statistical question with numerical data, statistical question with categorical data, and a non-statistical question with categorical data. So the majority of us thought categorical data. Would someone who say categorical care to explain why? Kyron?
What you said, cause you're not, I deal with numbers.
Okay, now be careful. When we talk about categorical data, does that not deal with numbers whatsoever?
It
Huh?
does, but you have to figure out what the question is meaning when you ask. Like, does it want you to respond with a number or?
True.
So remember, it's not just about whether it has numbers or not, it's what kind of response is it? Does the response fit into a category, or is the response numerical, in the sense that it's a measurement or a calculation, right? So if you were to ask me, hey, Mr. Kenny, what is your favorite board game? The answer, hands down, is a board game called Scythe. Is that going to be a category, or is that going to be a number? Numerical value. That's a category, right? Okay. If you want to ask me during enrichment tomorrow, I'll be more than happy to tell you why. I love that board game. All right. So is this a statistical question or non-statistical? We still have a few more who said non-statistical than statistical.
Because we're only asking you the question.
Okay, why is it important that you're only asking me the question?
Because it's about you.
Say it one more time.
Variation.
There's no variation, there's no variability. Remember, for it to be a statistical question, there has to be some element of variability in that one response can be different than another response, right? now that you know, if anybody comes up to you and says, hey, what's Mr. Kenny's favorite board game? The only response you should give them is Scythe. There should be no variability in the responses. How dare you? That board game is trash. Alright. Ready to get to today's lesson?
Is Uno a board game?
Is Uno? No, that's a card game.
Ah, shoot, they might need to stay in school.
That's exactly why you need to stay in school.
Hey, use that.
Alright, so here's our agenda for the day. We're going to do we're going to get back to equations and inequalities review, practicing our classroom culture and also making sure we understand equations and inequalities better. Hopefully we should completely finish lesson 6 equivalent equations, not expressions. And then we have a break to ask homework questions. And then hopefully we get most of the way through lesson 7. I don't imagine we'll get to lessons 8 and 9. That'll be the focus of tomorrow. Okay? So, let's see. Mia, can you read us our first objective today? Okay, we actually talked about this yesterday. What does it mean, because you should have notes on that page, that lesson 6, what does it mean for two expressions to be equivalent?
They look different, but are effectively the same.
Equivalent.
Effectively the same. Right? So equivalent expressions, which we saw this here yesterday, these two things looked different, did they not?
Yeah.
But every number that we substituted in for n gave us the same output, right? When we put in a 5, we got out, I think it was 8. When we put in a 7, we got out a 20. 13, we got 80. And then negative 4, right? So it didn't matter what we substituted in, we always got the same value out. That means that they look different, but they're effectively the same exact thing. They are equivalent to each other. That's going to go into our understanding of equivalent equations. Brianna, can you read our second objective for us here? Actually, you still need lesson 6, don't you? Because you weren't here yesterday.
Oh, yeah.
But go ahead and read us our objective, please.
No one can identify the moves that can be made to transform an equation into an equivalent one.
All right, so we want to figure out how can we create equivalent equations. All right, so that's going to be important here. Caleb, can you read our last objective?
Understand what it means for two equations to be equivalent and how equivalent equations can be used to describe the same situation.
All right. Equivalent equations are the foundation of everything that you do when you solve an equation in math. It doesn't matter how easy the equation is or how complicated the equation is, the fundamentals come back to the idea of equivalent equations. So we need to know what kind of moves can create equivalent equations and what it means for two equations to be equivalent and how that can help us find or identify a scenario in different ways. So let's get back to this activity, or this is what we started yesterday. One quick clarification, because this is something that came up very heavily in first block. Please notice, are these the same families? No. Do not mix and match these ideas. You got family A, where the youngest child is 7 years younger than the oldest, who is 18. You have family B, where the middle child is 5 years older than the youngest child. Okay? Remember, we are trying to write these ideas in as many equations as possible. We all clear on that? Okay? Please remember this word is right here. What should that make us think about? Equals, right? If something is the same, it's equal.
Interruption. We need Elena Woods and Jaden Sturdivant to come to the office.
Okay?
Elena Woods and Jaden Sturdivant.
The last thing I want to point out is this. When I come around to your groups, I am going to be asking you what your equations mean. There is a context here, right? Yesterday, I don't remember who did that in orange, but I see up there 18 minus 7, is equal to x, right? That is an equation. Yes, that is super abstract. There's variables and there's numbers, but that equation also has meaning. What does that mean?
It means that
X
He
equals
subtracted the youngest age from the oldest.
18 months.
Okay, but what you just said, does that have anything to do with this context right here? Anaya, what were you saying? What were you saying about this equation? What is this you saying?
He subtracted the youngest, well, it says it's the youngest child is 7 years younger than the oldest.
So-
So he knew that by subtracting that number from the oldest child, he would be able to find the youngest child's age.
That's what this equation is saying. I'm taking the oldest child's age, 18, taking away those 7 years to get the youngest child's age. Right? That is a really efficient way to say all of this. But we need to understand what these equations are representing, because every equation is going to tell the same story, but in a slightly different way. So, continue working on developing different equations for A. Once you get done with A, move on to B. Is that clear?
Yep.
If you finish B, move on to number 2 if we haven't come back to have a whole class discussion yet. Let's get to work.
I started on B, but I think I did.
And I would notice y'all are in different groups today. Talk with the people in your group to see if they had any other ideas than what you came up with yesterday in your group.
The A right, show it.